Hello, in this episode, I will talk about the concept of subbasis. So, in the previous episode, I talked about the concept of basis. The basis is basically a collection of subsets of X, which you can use it to generate the topology of the set X. And because basis has less requirement to build than the topology, sometimes it is more convenient to find the basis first, then use the basis to generate the topology. And here, the subbasis has a similar idea, which you can use the subbasis to generate the topology. But subbasis has even less requirement than the basis. So sometimes subbasis is very useful to build the topology. So let's look at the definition of the subbasis first. The definition of subbasis says that subbasis S for a topology on X is a collection of subsets of X whose union equals X. This means that the union of all the elements in the subbasis equals to the entire set X. So if we write it into mathematical equation, it looks like this. So the union of all the elements of subbasis. So if we let the S, the small s, to denote the elements in subbasis, and the big S to denote the set subbasis, then it looks like this. This equals to X. So this subbasis, we write it like this, big S. So this is the definition of subbasis, and because the reason why we need the subbasis is that we want to use the subbasis to generate the topology just like the basis. So a very natural way to do that is if we can make the subbasis into the basis, then we can use the method for basis to generate a topology on the subbasis to generate the topology. So based on this idea, at first we should understand what's the definition of the basis, and how can we change the definition of subbasis into the definition of the basis, so that we can convert the basis subbasis into basis. So if we can recall the definition of basis, it looks like this. It has two properties in the definition. The first property is that for any point X in the set X, there exists a basis element B from the basis B, such that it has the relationship like this: X in the B, and B is a subset of X. So this is the first property, and the second property is that if X is inside an intersection of any two basis elements, B1 and B2, B1 and B2 should from the basis, then we can always find another basis element B3 such that X should inside the B3, and B3 should inside the intersection of B1 and B2. Okay, those are the two properties in the definition of basis. So we need to convert the definition of subbasis into the definition of basis. How can we do that? If we look at them carefully, we can notice that the first property of the basis is actually equivalent to the definition of subbasis, and so we can prove it. So we see that the definition of subbasis is equivalent to the first property of basis. In order to prove this, we should first prove this direction. If the definition of the subbasis is true, then we can get the first property of the basis. And the way we do that is like if we assume for any x from the set X, then because the X, according to the definition of subbasis, it is a union of the subbasis elements. So because this is true, then X should be an element of this union, right? Then what can we get is X should belongs to one of the subbasis element from here, because this is a definition of the union operation. If one element belongs to the union, the element should belongs to one set in the union. Okay, so X should belongs to one set X, and we can give this set X a special name. We can denote it as Sx because it contains the point X, and because this Sx is from the collection big S, so it should be a subset of X. So this result is same as the first property here, this relationship. So it means we get this first property from the definition of the subbasis. Okay, how about the opposite direction? Can we get the definition of subbasis from the first property of the basis? So from the first property of the basis, we can get this relationship, so which is for any x in the X, we can have the relationship X should be inside the B, but because we are talking about the subbasis now, so we can replace the B by S. So we can have the X inside the S, and the S is the subset of the big S, X, and we can also denote this S by Sx because it contains the X. So now the question is, can we from this first property to get the definition of the subbasis? So what can we do is like this, because this relationship is true for all x in the big X. So like for any point, it means for any point x inside the big X, we can always find the Sx contains the point X. So how about if we do the union of the Sx over all the x in the set X, what can we do? What can we get? First, maybe we let this. We denote this by A. We call this union set A. And what is A? So first, A. We can find A should be a subset of X. The reason is any SX is a subset of X, because according to the definition of subbasis, is the elements of the subbasis are the subsets of X. So any SX inside this union is the subset of the X. So the union of subsets of X should also be a subset of X. It will not be bigger than the set X. So this is true. And also we can find A should contain the set X. This is because for any element in the X, for any element X in the big X, we can always have that this X is inside the set A. This is because in this union, any X inside the big X, it is inside one of the subbasis element as X. So when we do the union, it contains all the points X in the set X. So according to this relationship, we get this relationship between A and X. So A contains X, and from those two, we get A is actually equals to X. So this relationship just the definition of the subbasis. So we proved this one. So based on those two, we can say the definition of subbasis is equivalent to the first property of basis. After that, we need to consider the second property of the basis. So here, because we already proved that the definition of subbasis is equivalent to the first property of basis, then we cannot do too much on the definition of subbasis anymore to include the second property. But what can we do is we can modify the method we use to generate the topology by the subbasis so that the method can contain the second property of basis. In this way, we can convert the subbasis into basis and use it to generate a topology. So what should we do is use the second property of basis to combine it with the method for basis to generate the topology. Then we use this combination to build the method for subbasis to generate the topology. Then if we use this new method with subbasis to generate the topology, we can get the same result or similar result as a basis. So this is a basic concept. Now the problem is, how can we combine those two things together? So first, let's look at the second property of the basis. So this property means that if we have like two basis elements B1 and B2. Then, if there is a point X inside the intersection of those two basis elements, then there should be another basis element B3 such that the B3 is inside the intersection and it contains the X. Okay, so this is the second property of the basis. And now because we already have the first property of the basis for the subbasis, so in order to convert the subbasis into basis, what we need to do is to make the subbasis to satisfy this property. And what can we do? What should we do is to find this B3 and to satisfy the relationship that X inside the B3 and it should inside the B1 and B2, the intersection of those two. So when we convert the subbasis, what we should do is, like for any S1, S2 from the subbasis, if there is the X, what is the S3? So there is a very natural way we can define the S3 to let it satisfy this relationship in basis. And that is, if we can let S3 equals the intersection of S1 and S2 like this, then the S3 will always satisfy this relationship. This is because for the first part, because S3 is the intersection, this intersection, so for any elements inside this intersection, we can always have the relationship, the X is inside the intersection and it is equal to S3. And then because the S3 equals to the intersection of S1 and S2, then it also means that S3 should be a subset of S1, the intersection of S1 and S2. So those two things are satisfied, then the S3 will always satisfy this relationship. So in this way, we converted the subbasis and make the subbasis to satisfy the second property of the basis, and then now the subbasis has been converted into basis. And then what we need to do is use this converted subbasis to generate the topology with the method for the basis. One very good method to generate the topology by the basis is the lemma 13.1. It means that we can generate the topology T by defining the topology T by the collection of all unions of elements of B. If we write it into mathematical form, it is just like this. The topology T is just the collection of all possible union of the basis element B, such that B from the basis like this. Okay, but this is for this is how we generate the topology from the basis. If we want to generate the topology from the subbasis, we need to do the union of S, and we need to know what is the S, right? And the S should be the elements of the modified subbasis, which satisfy the second property of the basis. So here, the S, because when we modify the subbasis, we define the new element S3 here. The S3 looks a little bit different from the S1 and the S2, which S1 and the S2 are the normal elements in the subbasis. So here we have like two different kinds of subbasis elements. So one is S1, S2, and we also have S3. But actually we can define the elements of subbasis in a same way, such that we can include the S1 and the S1, S2, and S3, those different types of elements in one definition, which is if we just define the elements like the S3, which is for S3 we know that for S3 we say it is the intersection of S1 and S2, and we also can say S1 is actually the intersection of S1 with itself. Similarly, S2 is the intersection of S2 and S2, right? Then, based on this idea, we can say for any element, S I, and not I, just S in the subbasis S, we can define it as the intersection of Si with Sj, and the Sj are from the subbasis. So in this way, we make the different types of elements into the same form. So now with this method, we can do the union now. So here's how we do that. So this S just from here, S equals the Si intersect with Sj and the Si, and the Sj are from the S, right? So this is how we generate the topology from the subbasis. Okay, so if we write this in a formal way, it's just like this. The topology generated by the subbasis S is defined to the collection T of all unions of finite intersections of elements of S. So all unions means all possible unions. Here we have the unions of finite intersection, because we only consider the intersection of two elements, two subbasis elements. So it's finite. It's similar to consider intersection of 3 or any finite number of subbases, but we need it to be finite. So finite intersection of elements of S, which is the S, the small s. So in this way, the subbasis can generate the topology. Okay, so this is the concept of topology, and thank you for watching this, and see you next time. Goodbye.